So Kirchhoff's voltage law states that the algebraic sum of the voltages around a loop in a circuit is 0. So if we draw on a circuit here with some generic elements, and we give them some names, so let's say we have V1, V2, and V3, and then we also just kind of assign polarities. Polarities will be important when we're doing this. Basically, as you go around the loop, it will determine whether we add or subtract for our net balance of voltages. So the convention is to go clockwise around a loop, but it doesn't really matter as long as you're consistent. But all you have to do is when you're going around the loop, when you come to an element, if you enter the positive terminal, then you treat it as a positive, and if you enter the negative terminal over here, you treat it as a negative in the summation. So basically we would have negative V1 plus V2 plus V3 all has to equal to 0. And this ensures that the voltage returns to the same point as we come around the circuit. Now this works if you have multiple branches as well. Let's draw on another branch. So if we had, say, V4 and V5, and let's say one of them is like this and the other is like that, then when we go around this loop, we would enter V5 through the positive terminal, so we have a positive V5. Then we enter V3 through the negative terminal, so we have minus V3, and then minus V4 because we enter through the negative terminal when we're going this consistent direction around the loop. And that all has to be equal to 0. So this is going to be a very useful tool for us when we basically get further into analyzing circuits. It's just one of the many things that we have available to us to help solve for unknowns. So to keep this introduction simple, let's get rid of the right-hand loop. And let's say that we know 2 of the voltages. Let's say that this one is known, it's 9 volts, and that this one, V2, is known to be 3.6 volts, and we're asked to find what is V3. Well, we can plug those right into our expression. So we have negative 9 volts plus 3.6 volts plus V3 is equal to 0. And we can just rearrange that to get V3 is equal to 5.4 volts. Now let's say instead of generic elements that V1 is a voltage source and that V2 is a resistor, and same with V3. And if we knew that the current, let's say, was, let's say 1.8 amps, then if you wanted, you could find the individual resistances of each resistor using Ohm's law. So we have V equals IR. We can rearrange that to have R equals V over I. So let's solve for R1 first. We have R1 is equal to V1 over I. They're going to have the same current because this is a series circuit, so there's only one path for the current to flow. So we just have 3.6 volts divided by 1.8 amps, and that gives us R1 to be 2 ohms. Then we can do the same for R2. R2 is just equal to V2 over I. So that's going to be 5.4 volts over 1.8 amps, and that gives us a value for R2 of 3 ohms. But the point of this video isn't really to discuss how to find the resistance of these resistors, is to talk about the voltage basically returning to the same value as you go around the circle. So if we were to ground the bottom node, let's clear up some space down here, then we can write on the ground, label it on, and this is basically going to set this entire node to our reference point of 0 volts. So let's actually identify all of the nodes that we have. We're going to have this node that's grounded, which is everything until we hit the other elements. We're going to have a node up here, and then we're going to have one other node over here. So because the blue node is grounded, we're declaring that one to be our reference of 0 volts. Then when we go around, starting at this point, anywhere on the node really, when we go around, when we cross the battery, it's going to jump up 9 volts because basically that's what batteries do. The negative terminal is 9 volts less than the positive terminal. So this whole red node is going to be 9 volts. So we can label that on. And then coming onto this resistor, we drop by 3.6 volts. So 9 minus 3.6 gives us a value of 5.4. So this whole node has a voltage of 5.4 volts. And then when we come across resistor 3, it basically drops by 5.4 volts, and we end up back at 0 volts where we began. And that's the point of Kirchhoff's voltage law. You know, if we came back and we ended up with something that's not 0, then this wouldn't make any sense because this can't be 2 different voltages at the same time. So you have to come around the whole circle and return back to the value that you started with, and that's basically the same as saying that the algebraic sum of the voltages around the loop is 0. So hopefully that's a good enough introduction, and I will see you in the next few videos, and we'll do a few more complicated examples using Kirchhoff's voltage law.